Welcome to the second half of the lecture. So in the previous part of the lecture, we introduced impedance. And in particular, we said that to deal with capacitors and inductors in the Laplace domain, we would treat them in the same way algebraically as you would resistor networks in the time domain. But there was one caveat to that. We always assume zero initial conditions. So now in this particular class, I'm going to show you, or in this half of class, I'm going to show you how to introduce initial conditions into your Laplace method to solve circuits. Okay, so let's get started. So just as a quick refresher, we said that when we have zero initial conditions, what we were going to do is we would be able to replace our IV relationships for both the capacitor and inductor by introducing this concept of an impedance. So in particular, if you assume zero initial conditions, these would be zero. And so then we could change this IV relationship where I equals 1 over Z times V. And that would give us that S times C is 1 over C, or that the impedance for a capacitor would be 1 over SC. And then same thing for the inductor. The voltage equals the current times the impedance. And so in this particular case, we would have that the voltage equals SL times I sub S. And that would be kind of, SL would be our impedance for an inductor. We also introduced the admittance, which is just analogous to the conductance. So it's just the admittance is always 1 over the impedance. Okay, but now what about when we have non-zero initial conditions? And that's what we're going to talk about next. So when we have non-zero initial conditions, as it turns out, we have choices as to how we incorporate these non-zero initial conditions. We can either introduce the initial conditions as an additional source to our impedance, and that source can either be a current or a voltage source. So the ones on kind of here are the capacitor models, and then inductor models. And so if we introduce the voltage source, it's going to be in series with the capacitance, the impedance of the capacitor or inductor. And if we introduce a current source, it's going to be in parallel with the impedance of the inductor or the capacitor. And in each case, we define this source so that it reproduces this Laplace transformation of the IV relation between the capacitor and the inductor. So that's basically what we're going to do. We're just going to take our impedance model and we're going to add a source to it in order to model the effects of the initial condition. In the next few slides, I'm actually going to derive these models, and it's actually quite simple. So let's get started with that. Okay, so first we're going to look at the series models. So if we look at this particular circuit here where we have an impedance in series with the with a current source. One second, my pen is not working. Okay. We can basically find what the current going through the circuit is by kind of intuiting that this is actually Vs and then this is V0. And so the current I0 will actually be equal to V0 minus Vs divided by the impedance. We can also find the voltage V0 using KVL, and if my pen decides to work. Okay, using KVL as V0 will be equal to I0 times Z. So this, the voltage from here to here, I'm going to call this VZ, plus the voltage from here to here, which is just Vs. So this circuit that I showed on the left, that's basically the IV relationships for it. Now what we're going to do to define our models, we're going to try to use these two expressions for IO and VO to match our IV relationship. So first I'm going to derive the capacitor one. So for a capacitor, we had that I equals the capacitance times ddt of the voltage across the capacitor. Okay? And the Laplace format of this would be that I sub s equals the capacitance times S V sub s minus V0. So this is at time equals 0. Time equals 0. Okay, now in this particular case, we have something that looks like this, where you have I on the left-hand side, and then something that multiplies it. So we're going to modify this expression so that it looks more like the one on the left. And to do that, we can simply factor out an S from this expression. So we're going to have that S times C times V sub S. Oh God, here, let me just erase really quick. What's going on here? Okay, so delete, delete, delete. So this is capacitance, parentheses. Here, I'm going to draw them like this so that it's clear as parentheses. Minus V sub 0 over S. And if we call Z as equal to 1 over SC, and if we define the Vs as equal to V at time equals 0 divided by S, then we're going to get that this is actually equal to V sub S minus Vs over Z. So I'm just going to define this as CZ. So for the capacitor, we can simply choose our impedance as we did in the previous lecture. And we just need to add this source in series that's equal to V0 over S. Now for the inductor, we're going to do a similar approach, but now our IV relationship is that VL equals L ddt IL, which translates to VL sub S equals S times L IL sub 0 minus L times ILs of 0. Sorry, and this should be S, sorry, ILs of S. Okay, 1 second. So ILs of S. If this thing allows me to write. So believe it or not, digital pens run out of ink too. Okay, in this particular case, you can already see that if we call this the impedance, so if we say ZL equals SL, and then we say that that Vs equals negative L ILs of 0, then we're going to get that this expression says that VL sub S equals CL times I of S minus, well, here, this is still the inductor current, minus Vs of S. And so for the inductor, we can just replace this Vs here with negative L ILs of 0. So basically, for our circuit model, Vs will either be negative L I sub IL sub 0 or V0 over S, and this is going to be for the capacitor, and then for the inductor it's going to be negative L IL sub 0. Oh shoot, I meant to write inductor there, not LIL sub 0. So for the inductor. Okay, so that's basically how we're going to define our series model. In the next slide, now I've written everything more cleanly. So basically we said that if we looked at the Laplace transform of the current IV relationship for a capacitor or inductor, we can then basically do some kind of pattern matching. For the capacitor, we matched this expression. So we said that this is just really 1 over the impedance. And in that case, this becomes Vs, and then this is just V0, which is kind of the voltage drop across the two elements. And then for the inductor, we use the second expression, and so we said that we set this as the impedance C. This is IO, and then this becomes well, this with the negative sign becomes Vs. So the polarity for the inductor is reversed. So we have basically negative LIO. So as you will see in our models for the inductor, we typically write this source as minus plus L I sub 0 to take care of that negative sign. And for the capacitor, we just write it as plus minus V0 over S. Okay, so those are the series models. Now we are going to derive the parallel models kind of using a similar procedure. So if we look at this circuit here, we can see that the voltage drop across this inductor is equal to kind of the current times the impedance. So we're going to have kind of this current here, right, is going to be equal to IS plus IO. And then that times Z will give us VO. So basically we have that VO equals Z times IS plus IO. Sorry, IO. Now, in order to figure out what IO is, we have a current divider. And so IO is actually equal to V0 over Z, which would be a current going in this direction, minus IS, because IS is going in an opposite direction of IO. So basically you have a current going here, and the current going through the resistor, or the impedance minus the current of the source, is equal to IO. Okay, so now that we know that, we can actually try to use the same kind of concept as we did last time to derive what the sources should be IS for both the capacitor and inductor. So let's start with the capacitor. So for the capacitor, we're going to have, and I think I might have to pause these videos soon. So this is the last slide before I change batteries because my pen's becoming untenable. Okay, so we have B, so we have C dV dt equals I, so we have IC sub S equals C times S VC of S minus V sub 0, and typically we write plus here, but I mean it's a continuous quantity, so you don't really need to write it. Okay, so in this case, since we have IC on the left-hand side, we want to use this expression. So we want to factor out the impedance of a capacitor. So we're going to factor out an S from, from both, and we're going to get that this is just equal to SC, SC VCs of S minus C VC0. Now, this is actually 1 over CC, and so this actually becomes IS. So for a capacitor, we're going to have that IS is going to be equal to C VCs of 0, and CC is going to just be 1 over SC, like we have been using actually since 2K1, where you had to do phasors. Now for an inductor, we have that that the voltage equals L di dt. So we have the voltage equals L di dt. Voltage of S equals L SIL minus I0. Remember that this is IS of S. And so now we want to use this expression. So we're just going to factor out an S. And so we're going to get that this is just L times S IL of S minus I0 over S. And then this is just the impedance CL. And so that's going to give us that actually IO is actually negative I0 over S. So the polarity for the inductor is actually pointing away from the input IO. So this is IO or IL, and this is I0 over S. And for the capacitor, it's actually pointing up. So for the capacitor, so this would be SL, and then this one would be 1 over SC, resistor, and then you have a current source pointing up, and the magnitude of that current source would be C VCs of 0. So that's how we derive both models. So here's kind of done more cleanly. So the idea is exactly the same as before. We use these two IV relationships. For the capacitor, we have I on the left-hand side, so we're going to use this one. If we write it this way, this becomes the 1 over the impedance, and then this becomes our IS. And then for the inductor, we're going to use this one because V is on the bottom one, because V is on the left-hand side, and then that's going to give us that that SL times I sub S minus I sub 0. So that's going to give us that I sub S has a different polarity, and its magnitude is I0, the initial condition for the inductor current divided by S. All right, so that's basically how we're going to incorporate initial conditions. So just in summary, for the capacitor, we're going to have two models, and we can use either of these models when we analyze circuits that include the initial condition. One is where we replace the capacitor with an impedance for the capacitor in parallel to a current source equal to with magnitude CVCs of 0 and pointing up. Another one where we replace the capacitor with the impedance of a capacitor plus a voltage source in series, VCs of 0 plus, and then the voltage drop across the capacitor is the addition, of course, of the initial voltage plus the voltage drop across the inductor, and the current in this case would be the sum of these two currents going through the capacitor. For the inductor, we have a similar model, except now both polarities are in the opposite direction. And also for the parallel case, we have ILs of 0 divided by S. So remember for the capacitor, this was the voltage was the one that was the VC over S. And then the current becomes LIL, whereas for the capacitor it was C VC for the, sorry, the voltage source is LIL, whereas for the capacitor the current was CVC. So these are the four models we're going to use. Now I'm going to actually go over an example to show you how we're going to use these models. Okay, so let's say we wanted to analyze this circuit in the time domain, and then we were told some non-zero initial conditions. So what we simply do is we're going to take this capacitor to convert it into the Laplace domain. We're just going to use that equivalent circuit model. And now we can just apply KVL around this loop. And so we're going to have, in this case, did I apply KVL or KCL? The Vn minus Vc over R Yeah, so here all I'm saying is actually that Vn minus Vc, which would be the voltage here, divided by the resistance should be the current. So Vn minus Vc divided by R is the current, but that's also equal to that's also equal to C ddt of Vc. So we can actually write the expression here, and then we can actually solve for Vn of S, and we're going to get the same equation. Yeah, so actually that should be also equal to kind of negative Vc of S minus Vc0 over S divided by the impedance, which is what I wrote there. As you can see, they both agree, so this does work. Let's look at another example. So this is the circuit we solved in the previous class. Now we're going to actually rewrite the circuit, but now including initial conditions. In this case, we have a circuit that has a lot of things in series, so it makes sense to use our series representations. So we're going to replace the inductor. So we have 1 over S plus 3. And then the inductor is replaced by an inductance and a voltage source. And the capacitor is replaced by a voltage source. And this voltage source will be plus minus, and we see it was going to be C Vc of 0, and then this is Zc, and this one, so this is Cl. So remember that for Cl the polarity is reversed, so the negative should always be pointing away from Cl. So in this case, this is plus minus Vl, plus minus Vl. And then the value should be ILs of 0 divided by S. So this would be the equivalent circuit we would have to solve in order to include initial conditions. So here I kind of wrote things more cleanly, and I think I actually made a mistake in the previous slide because this is actually ILs of 0, and this is VCs of 0 divided by S. But the polarities are correct, and so this would be kind of the positive value for VL, and this is the negative value for VL, and then this would be IL, and then this is plus minus VC, and IC would be flowing down here. So it's important you keep track of the polarities because you have to connect these sources in the right polarity. Otherwise you'll get the wrong answer. So that's why I'm making sure that I label everything. Okay, so if we want to analyze this, so if you had basically plug this in backwards, when you applied KVL, you would get your equation with the wrong sign. So that's why you have to make sure you use the right polarity. Okay, so now let's apply KVL. So we're going to have, remember, whenever you exit on a positive sign, that means that you insert that voltage with a positive sign. So we have 1 over s plus 3, and then you have minus, which is a voltage drop from here to here, which is the impedance of the inductor times IL, or the current going through the inductor. Then here you enter in the negative and you exit out in the positive sign. So it's a positive sign, L ILs of 0. So this is L times ILs of 0. And then here you have a voltage drop across this impedance. And so you have 20 over S minus 20 over S, ILs of S. And then finally here you exit through the negative sign, so there should be a negative sign here. And it's VC sub 0 divided by S. And that should all sum up to 0. So now we had just derived the differential equation for this the Laplace representation of this circuit. And now we can solve for ILs of S. So we're going to move all terms that don't involve ILs of S to the right. And then we can just divide everything by this to get our final S representation of ILs of S. So in particular, it's going to look something like this. Now, one thing that you can already notice is that this term here, we already know what it is because we solved it in the previous lecture. So we actually only need to inverse Laplace the second term and add it to it. So this is actually what people would call the zero state response, because it corresponds to the solution when there is zero initial conditions. And this would be what people would call the zero input response. And next lecture, we're going to talk a lot more about this, because it's the solution where the initial conditions are the ones driving the circuit. So this would be kind of the zero input response, which is actually this one once you plug in the initial conditions. Okay, so in the last lecture, we found this. So I'm not going to do that derivation again, but here's kind of the answer we found in the last lecture. And now we just need to inverse transform the second term and add it to our solution. And so in particular, here I go over that inverse transform. So you basically apply the same trick as before. And just remember that B1, 2 times the real part of B1 will give us the cosine coefficient. So 2 times 0.5 is just 1. And then 2 times the real part, the imaginary part of B1 is actually the sine coefficient. And since it's negative here, it has to be negative there. And so that gives us kind of the final solution to our circuit. Yeah, so that's how you incorporate initial conditions. Effectively, all we're going to do is just add sources to our equivalent circuit models. And then for series configurations, you want to use that series representation. We could use the parallel configuration. We would get the same answer. They're both algebraically equivalent, so it doesn't really matter. And yeah, that's all I have. So when you analyze these circuits, like I said, in this particular case, in order to analyze this, you would use this particular equivalent circuit to replace your inductor. So you would have basically plus minus 1 over S. 10 is the impedance of a resistor. The impedance of an inductor is SL, so 5S. And then here is where you have to kind of remember that the, well, if you assume that polarity of VL is this and then IL is going down, the minus sign is usually the one that's closest to the inductor. So this is the correct polarity, and then the magnitude is L ILs of 0, so in this case 5. And then they told us ILs of 0 is 2, so it's just 10 volts. Now you can actually just solve this circuit to get the solution. So I do that in the next slide. So this is kind of what I drew in the previous slide. And you can apply, in this case, I applied KCL, where I said that this is the impedance of the circuit, which is just 5s plus 10. And then the voltage drop would be the voltage here, which is actually negative 10, minus the voltage here, which is 1 over s. And so we have 1 over s minus minus 10 gives you 1 plus 10 s. And then, yeah, so it gives you this. Then I multiply both the top and bottom by s. And so I got this. And now I had to do partial fraction decomposition to get it into this form that's more amenable to lookup in our Laplace tables. So the final solution will actually be 1 over 10 u of t plus 19 over 10 e to the negative 2t u of t. And that's it. We just solved this circuit. Okay, so that concludes solving circuits using Laplace transforms. Next lecture, we're going to go over decompositions of the Laplace response. And then we're also going to introduce the transfer function, which is a very important concept. And then after that, we're going to actually start going into more global properties of circuits. So we're going to stop actually trying to analyze circuits, and we're going to start transitioning into designing circuits. But before we can do that, we have to start looking at circuits from a more meta perspective, or looking at its global properties. Okay, so that's all I have for today, and I'll see you later.